Okay. Okay. Good morning, everybody. It's conventional to say it's a pleasure and a privilege to introduce the speaker. And in this case, it's a pleasure and a privilege and an honor to introduce the speaker for reasons which I'm about to explain, even though you probably know why anyway. John Houghton has been one of the most influential people on the planet in alerting humanity to the dangers of climate change. I was fortunate in my career that John was my tutor in physics as a student, and therefore, in a sense, he has been a guiding light to me for much of my career in many ways. He started his career, he started as a lecturer, but then he was professor of atmospheric physics and founder of the Department of Atmospheric Physics at the University of Oxford. But then he later went on to, while he was there, he initiated many space experiments in connection with meteorology, both terrestrial and planetary meteorology, sending space probes to Mars and so on. And then he became the director of the British Meteorological Office, which is the agency responsible for all weather forecasting in the United Kingdom. He was the founder of the Hadley Centre, which is a major world centre for computing connected with climate. And he was, as I said, one of the main impulsors of the International Intergovernmental Panel for Climate Change, and the president of one of its technical commissions for over 15 years, and responsible for the highly competent and meaningful reports that the Commission produced, and which have had some effect in persuading people. They've had a lot of effect in persuading open-minded people that climate change is real and that the human effects of climate change are basic. Well, I've spoken enough. I could have said a great deal more. But that would be pretty stupid at this time, because we want to listen to John himself talk to us about climate change, and I'm sure that afterwards you'll be open to questions about climate change, right? Yes. Okay. So please go ahead, John. Give your talk.
Well, ladies and gentlemen, thank you very much indeed for your welcome this morning. It's a great privilege to come and visit your outstanding institute. I had an outstanding day yesterday, visiting La Palma, and all that's on La Palma, in the glorious sunshine too, and it was a very interesting day. I was catching up with astronomy as far as from my point of view, because I haven't been involved in astronomical things for many years now. And it was a great privilege, as I say, to learn about what's going on and the wonderful way in which things are advancing in this tremendously exciting, complicated, unfathomable area of that sort of thing. I spent most of my life looking down and not looking up. That's looking down from space towards the Earth and all that you find on the Earth, and not looking up to space. it's much bigger, of course, on the outside, but looking down has enormous complication and enormous wonder too. And our ignorance is very great in that area as well. I sometimes say about science that that science is not something you go into and you learn a lot of things about it. And when you look back, you say, I've learned a great deal. But one thing I've learned is that there's even more to find out than I knew. So it's a completely expanding area of human knowledge. And it's not, the more we learn we don't know. And that's true of what you're doing in the astronomical area, and true also in the area that I've been very concerned about in my life. Well, I'm going to talk today about climate change, what we know about it, and how we might learn something about what's really happening to our planet, and indeed what we humans are doing to it. It's a very big problem, one of the biggest problems the Earth faces, and it's causing a collision in the world between science and politics. Because scientists and politicians don't always talk the same language or behave in the same way. And so it's a very interesting area to be, not only interesting, but also actually vital for our world. So let me start going very quickly through. Most of you will know a lot about it anyway. So we'll start about the underlying physics of global warming, as it's called. Radiation comes in from the sun to warm the Earth's surface. That is balanced by long-wave radiation going out from the Earth's surface, which in the absence of clouds, some of that gets out to space, but some of it doesn't, because it's absorbed by gases in the atmosphere called greenhouse gases, most important of which is carbon dioxide, but it's also methane and nitrous oxide and some other minor ones too, which is stopping that radiation getting out. And that means that the absorption of that radiation on its way out means that to restore balance to the whole system has to gain in temperature. It's like having a blanket in bed. If the blanket gets thicker, you get warmer at the bottom, and the top part can tend to get colder. And it's studying that and realizing how that behaves and how that works that's very important for us. Well, that's the spectrum in the infrared, which is the visible radiation is on the left of that diagram, of course. And here's there are some gases there which are absorbing radiation. On the way out, you've got carbon dioxide, which is the most important. You've got methane and others. And that's how they're becoming blankets over the surface, and therefore increasing the surface temperature. And that's the whole business that we're talking about in this lecture. Now, carbon dioxide, of course, has been in the atmosphere a very long time. It's been there for millions of years. That's the last 10,000 years. Parts per million was about 270 or so until the year 2000, 10,000 years ago. It's kept pretty stable for a long time, for most of that period, until about 200 years ago, when we began to burn coal, and then oil, and then gas. And enormous quantities of carbon dioxide have been put into the atmosphere to satisfy our ongoing thirst for fossil fuels. And this is an old slide, of course, because we're now up to 400 parts per million in terms of carbon dioxide. And also, if you go further back in time, the carbon dioxide has not been anywhere near 400 parts per million for millions of years. So we really are changing something very fundamental to one of the fundamental parameters of what's here on Earth. Just to try to explain how this works, the figure on your left gives you sun from the sun. We are getting 240 watts per square meter on average. And if it's in equilibrium, then 240 watts per square meter on average goes out from the infrared part of the spectrum to balance it all out. But then suppose all of a sudden the CO2 goes up by a factor of 2. We're not there yet, we've only gone up by less than that. But if it went up by a factor of 2, then the radiation coming in from the sun would be the same. The long wave radiation going out would be about 4 watts per square meter less, 236. And the result of that is, in the third column, you will see to get back to 240 watts both ways and have something in equilibrium, and the temperature of the surface, if nothing else changes at all, then we need to increase the temperature of the surface by 1.2 degrees on average. But then other things do change. There are feedbacks which occur in the system. One of the most obvious of those is the water vapor feedback. If you warm the surface, you get more water vapor in the atmosphere, and water vapor is also a very strong greenhouse gas. And there are other feedbacks of a similar kind. And in the end, if you add the feedbacks in, the average temperature goes up by something like 3 degrees for double carbon dioxide. And most of the research that's done thinks that's quite a reasonable number. And then we're back in equilibrium again. But to get back to equilibrium again will actually take a very long time. I'll explain about that more in a minute. So how do we learn about the details of the climate change I'm talking about? We have observations. We need to observe the whole of the climate system. And that's a very big thing to do, because it's not just the Earth's surface, it's not just the atmosphere, it's not just the oceans, it's also the land and everything that happens on the land and all that we do to it one way or another. And we have to do a great deal in observation. And then we want to try to simulate how the whole thing works on computers. Well, the only way to simulate it is on computers, of course, because we have no other ways of doing it. It's all nonlinear, very severely nonlinear in many cases. So I have to do computer modeling. Let me quickly take you back to a day in my life that I remember very well. 1957, when the first Sputnik went up. And I was working in a research lab, I won't explain where, and all of a sudden, I realized, and other people realized, that there was this thing out there which was spinning around the world and observing a large part of it. It wasn't quite in a polar orbit, but it was observing a large part of the atmosphere, the oceans, and all the rest of it, or could observe it twice a day. And here was me trying to make measurements in the atmosphere from balloons and aeroplanes and that sort of thing to try to get some coverage in the vertical and in the horizontal. And of course, struggling with doing anything more than something that was very local indeed. How could we begin to observe the whole of the system and the way it circulates, the way in which all the variations we have in the atmosphere, how they circulate and influence each other, northern and southern hemispheres and all that sort of thing? How could we conceivably observe all of that? Here was a conceivable answer. And some of us began to talk very loud, very hard, actually, about how on earth we could put something on something like Sputnik to do just that. And of course, that was the beginning of space observations, and you know all about it. That's a picture from a geostationary satellite, and showing the enormous detail you've got just in the cloud systems, never mind about what's in the structure of those, of the atmosphere itself, and the various things that are going on, and the way wind systems develop, and so on. So I began to put a lot of effort, a lot of thought into remote sounding of the structure of the atmosphere's temperature from space. And in 1970, together with Desmond Smith, who was in the University of Reading then, I'd returned to the University of Oxford. We worked together on a simple instrument, We called it a selective chopper radiometer because it was a rather clever way of actually getting enough energy in the infrared part of the spectrum to make temperature measurements at a whole variety of levels in the atmosphere. And in fact, that's the 4th of August 1975, we had instruments on Nimbus 5 and Nimbus 6, the later Nimbus satellites. We were able to observe to some degree, to a good degree actually, the whole temperature of the atmosphere, not only near the surface, but right up to 90 kilometers up, and also across the whole of the surface. So, and there's the average temperature, averaged around latitude circles, of course, for a particular day, 4th of August 1975, as measured by these rather simple, rather elegant instruments that we've been able to make in our work, which was with NASA. But I'll come much more towards the present day now to get really into this climate change issue. And there we see, of course, global temperature is now measured by all sorts of means, but by all sorts of satellites too. There are lots of satellites up there measuring temperature from space in all sorts of ways. And there we have the average temperature over the Earth. And the later parts of that diagram, of course, is in the space area from 1970 or so onwards. Before then, it was also measured as far as we could around the world. And since 1970, the temperature has risen very steadily, and we believe that is very largely due to the human influence of climate change. But then it isn't just the average temperature around the whole world we need to know. We need to know the temperature of the surface, and that's, if we go down to the 1950s to the 2000s and compare the temperature at the beginning of that period with the temperature at the 2010 or so, which is the last data on which this was created. And you can see that the whole world is warming. Almost. There are some blue patches near the Antarctic, where, in fact, over that period it wasn't warming. So the atmosphere is not a well-behaved system. It doesn't follow everything that's happening, but the vast majority of the world is warming. The Arctic regions are warming faster than much of the rest. And the oceans, of course, are warming more slowly because of the thermal capacity of the oceans is very much greater than the thermal capacity of the atmosphere. More of that in a few minutes. But you can see of course, it's not a uniform business, and it happens in different ways in different parts of the world. But nevertheless, the average is going up at this steady rate of it's now something approaching a degree since the warming began, so far as human influence was concerned. If we go to the Arctic regions, then you've got that's a map of the Arctic on the end of 21st of September 2012. That is that holds the record at the moment for the least ice. It's the ice coverage in the polar region, of course, is least in September at the end of the summer. If you average the ice over the period from 1979 to 2000, that is there as a sort of rather pink line, rather vague pink line, which you can see on that diagram. Since then, the ice at the end of the summer has been retreating very rapidly, and it's now as what there. The people who were trying to extrapolate that as best we could a few years ago was suggesting that by the end of the century all the ice would have gone. Now people are saying, well, we think it might well happen by 2030 or even 2020 for the whole of the Arctic ice to disappear at the end of the summer. That's more rapidly than any of us expected or even or managed to try to advance. And the people, incidentally, who are rubbing their hands with glee over that, guess who they are? They're the oil people. There's oil up there. So by getting rid of all that ice, we're opening up a major problem also with how we solve the problem of not using oil. More of that later. Well, that's observations, and I've gone through that very rapidly. We can now make observations with great precision and with a good degree of coverage, and plotting charts from space observations which are less than world charts, that is, which are perhaps a kilometre and their grid size. And that really is, of course, because we've got much more computing power than we ever had before. And computer modelling is, what do we do when we computer model? Most of you will know about this, and I need to explain it to you. But we integrate the equations of motion, the equations of state, describing all the climate-sensitive parameters. And that's an essential tool for bringing together all these non-linear processes, which and the positive and negative feedbacks, which are built into the system. And it's the climate system, and that's a small part of it in a way. It's not describing it all by any means, but it's giving you some idea of what's involved. We've got changes in the sun, which are there. We've got changes in the composition and the circulation of the atmosphere. We've got changes in the content of the atmosphere. We have aerosols, these dust particles, or particles which are created from emissions, from pollutions, and all sorts of other places. And they have put a very considerable effect. More about that in a bit. And then the biosphere is involved. The atmosphere and the biosphere get to have a relationship. The soil matters too. In the CO2 content depends very much on whether the land is absorbing carbon dioxide or emitting it. Depends very much on the soil and the way you're farming and so on. This is a very recent area of research. And the sizes of the outputs into the atmosphere or the sinks of CO2 in the land are much larger than we ever expected. So that's a big area of research also at the moment. And then there's the cryosphere and the snow parts and the sea ice and the ice sheets which are disappearing and so on, which are occurring there. And then there's the coupling with the oceans, a bit more about that in a minute also. You can imagine having to try to simulate the whole climate story on a computer is a major and difficult operation because you have to make so many assumptions in doing that. But thanks to the power of computers, of course, then having understood all those things in the system, you have to solve the equations of motion, which involve the density and the motion and the water vapor in the atmosphere in particular, the exchange of all those things across the ocean-atmosphere boundary, and then you won't have to do the same thing for the oceans, exactly what's happening there, and that's what we're beginning to do on a larger scale than we ever did before. Well, you'll know about computers and how far this is not the latest diagram I've seen of this kind, but it's almost one of the latest. But the power of computers has been going up by a factor of 10 every 6 years ever since 1950. And it's actually a remarkable straight line. How long that will continue for, we're hitting some big problems as we get to faster speeds, because you're getting down to, because of the size of the basic, you're getting almost to atomic sizes by the time you try to do computing. It's at faster speeds, but that enormous increase, which now we have computers which are petaflops in their power, and it's those sorts of computers and and meteorologists are very thirsty for bigger computers and faster computers because it's still limiting a great deal of what we do. Going back to the average temperature now, and how can we, what are we going to do when we've got these computer simulations? Well, there's an example of computer simulations of the past climates over the 20th century. On the left-hand side, you've got a simulation which is simulated in red on the left, and that takes account of all the factors which we know about so far as we are able to put them in. And you will see that there's not perfect agreement because, of course, there's a lot of variation in the way the Earth's temperature behaves from year to year and from day to day and so on. But then on the right, the one on the right omits all those factors which are human-induced because of the increase of greenhouse gases. And there's no way you can simulate the climate from 1960 onwards without introducing all those things that depend on greenhouse gases and the like. And that's a pretty convincing story because it's something we've got from the past that we really have to take everything into account, and that we're making quite a big difference to what's happening on the Earth. Well, I don't know if you can see all those very well, but this is now taking local, very similar calculations to the one I've just shown you. But these are now taking various localities over the different parts of the world. There's at the bottom, you've got the global averages of land surface and land and ocean surface, and the ocean heat content, and I'll more about that in a minute. And then the others are either pictures of the bottom one's the temperature, but many of the others are ocean heat content to do with the oceans, because the oceans are warming up too, and we're getting measurements of those. And the dark lines are the observations, and the pink lines are the simulations. And the blue ones are simulations without greenhouse gases. And you will see the sort of diagram I showed you for the whole globe is reproduced as one looks at different parts of the Earth's surface, which makes you feel that you're on the right track in the way in which the whole of this science is going. So that's the physics and the simulation of climate change and climate change for human reasons. So what are the main impacts of that so far as we're concerned in the real world? There are three of them I want to mention. The first is the increase in average temperature, and that means that we're going to get more heat waves. The way it will hit most human beings is in terms of more hot weather around the world in different ways. Well, that's the average temperature for the 2050s as simulated by computers. And with the sort of increase in greenhouse gases that's going on at the moment, and not assuming enormous rises above that, but not assuming also that we're going to get rid of it very fast. And you will see that the land, of course, is getting a lot warmer than the oceans. The sort of temperatures we're talking about in different land areas are average temperature changes of up to 3, 4, or 5 degrees Celsius in different parts of the world. Now that's an enormous change in average temperature anywhere. So that if you look at some of those really warm areas, there's parts of Africa hot enough already in many ways. It will get hotter. Parts of Australia, they've had heat waves in Australia. Parts of Russia, and they've had big heat waves in Russia. And then the United States has seen very big heat waves, and so on. And these are a major problem, or likely to become a major problem. In Europe, in 2003, there was a very intense heat wave in the whole of that summer, actually, and which hit a lot of cities in Central Europe. The average the temperature, the daytime temperature, was going up to over 40 Celsius in many European cities for days on end. It's something that had never been observed before in any records that go back as far as you can go. It was completely outside the range of all the summers that had ever been observed, and it is estimated that about 30,000 people died prematurely because of that heat wave. So this is really beginning to hit normal people, and we haven't really got very far down the road yet of how these things happen. I could show you lots of pictures of this kind. There's many homes in Colorado Springs in June 2002 in the United States which were destroyed, and there was quite most people got away, but their houses didn't, and it was a very disruptive thing, and there are many of those been happening. The number of fires in areas where people are living, in Australia, in North America and elsewhere in the world, have begun to increase dramatically. Then there's warming of the oceans, and that's something we've not put a lot of effort into until about 10 years ago. We had, of course, measurements of the ocean surface temperature. We didn't know what was happening below the surface. And a lot of effort was put in internationally by international groups. And the Argo float system, this is taking thermometers, simple thermometers, but very accurate ones, which can drift their way through the oceans and can move up and down to 2 kilometers downwards to the top of the ocean. And then when they get to the top of the ocean, then they relay their bunch of temperatures to satellites, of course, who pick them up. And there have been 3,000 of these floats going around the world's oceans now for some 15 years or so, and trying to measure the rate of gain of heat of the oceans, which is something that's obviously very important, because a lot of the energy from this disparate problem, the disparate situation with the greenhouse gases, is going to go into the ocean. And indeed that happens, and the ocean, there's the heat storage in the ocean in the upper 2 kilometers. So that was the 2000 to 2008 period. And you can see there's a steady growth there of heat storage in the oceans. And this diagram tells you pretty well the story as we know it at the moment. This is from the latest IPCC report. This is the period from 1970 to 2010. There is the heat storage that is going into the upper ocean is in light blue, into the deep ocean it's dark blue, into the land that's comparatively small. There's ice there, also into ice, it's melting ice. It's going into the land, and finally it's going into the atmosphere. Now, that shows you that well over 90% of the energy, extra energy that's coming into the whole climate system as a result of greenhouse gases is going into the ocean. And that's a very interesting result, because it tells us just how fast the ocean is warming. And there's a lot of motion, of course, in parts of the ocean, move up and down and so on. And but that's the amount of heat going into 2 kilometers down is not very large at the moment. It's only about 1/100th of a degree warmer yet. The top of the ocean may be half a degree or a bit more. The bottom, the 2 kilometers down, is less than 100th of a degree. So it's going to take a long time for that ocean to warm up. In fact, it's going to take decades and centuries into the future. Now that's a serious result, because if we turn the carbon dioxide tap off today, and stopped putting any more into the system, any more greenhouse gases into the system, stopped it all warming so far as we could, this heating of the ocean will go on in order to bring the whole atmosphere ocean system into equilibrium. And that will go on for decades or centuries into the future. And we can't stop it. Or at least it would be extremely difficult to stop it. It would need a major effort of the kind it's already gone into the greenhouse gas system in order to try and get it backwards out of that. And that would be impossible to do on any standards. And that's a very big result for us, which we need to take very strong attention to. I was going to say something else about it. I can't just find it on my bit of paper. Just a minute. Yeah, so no, the next thing I move on to than this, of course, is to talk about sea level rise. As we warm the oceans up, so the oceans expand. And we're measuring sea level rise, and that's the situation from the last century or so. It's gradually increasing. It was going up by less than 1 millimetre per year in the early 20th century, going up by 2 millimetres a year in the later 19th to 20th century, and the situation now it's going up by over 3 millimetres a year. And that increase will continue as the oceans begin to warm and expand. And the best estimate we have for this century now as to what will happen if we carry on with fossil fuels as at the moment with greenhouse gases, then we are going to get about 1 metre of sea level rise this century on average. That allows also for, of course, melting of some of the ice caps, and melting of glaciers, of course, around the world also adds to it. But that's the situation, that's the red line. If we really try and do something about it, and the best we could conceivably do, we'll put it on the blue line, which is 3/4 of a metre on average worldwide. Now, imagine that problem to the world. Sea level rise going up by about 1 metre. I guess in the Canary Islands you won't be too badly off because you've got steep terrain around most of your land and so on, but it will have some effect around here. But go to Bangladesh. There's the 1, 2, 3 and 5 metre contours in Bangladesh. There are 10 million people that live below the 1 metre contour. And it's a very jagged, of course, coastline. It's very fertile because it's stuff that's washed down from the rivers. It's the population density is very high because people are farming there as hard as they can go. But where are those people going to go? There are 25 million people in southern China who are similarly affected. And incidentally, in Bangladesh, the Indians are building a fence around their perimeter to make sure they can't get into India, or at least to try to do that, because it's going to be a very major problem. And I could go around the world and tell you similar stories, but I won't. You can just imagine the problem of sea level rise, which is going to cause for many cities in the world that are almost below sea level, or 1 metre of sea level rise will make a enormous difference. And of course, in developed countries, we can try and build things around it, but in large parts of the world, you can't do that. at all easily, because there's not the means to do that, not the money to do that, and so it's a very major problem. And there's a Bangladeshi family on their way to try to find a new home. Well, that was the second thing I was talking about. The sea levels work in the ocean, but then what's going to happen about what happens in the atmosphere? Very simply, as the temperature increases, we get more water vapor evaporating from the oceans into the atmosphere. That water vapor will condense to form clouds, and the average rainfall will go up. And the average rainfall around the world is increasing at about the rate you expect. But when that condensation occurs, of course, latent heat is released, and that latent heat is a large amount of energy. In fact, it's the largest single source of energy for the atmosphere's circulation. So that means we have a more energetic hydrological cycle, more energetic motions in the atmosphere. There'll be more intense rainfall. In fact, the rainfall will tend to come down in bigger dollops. And incidentally, it also means that droughts may become more common too, because the air gets drier as you go up, and if you get more energy in the circulation, you get drier air in some drier regions of the world. And although that's not quite as certain as to what's happening to the wetter regions, there are more droughts coming in the world at the moment, which are very likely linked to climate change as well. There's a map of the likely rainfall in 2090, simulated by computers or projected by computers, and you can see we're talking about the wetter regions there are plus about 30%, and the drier regions are minus 30%, and the wetter regions are plus 30%. And Southern Europe is going to be one of the drier regions, and that's a major problem for countries like Spain. Will tend to get drier, and water will be scarcer, and the average temperature will be up. And there's the same thing happening in parts of Australia, Southern Africa, in the West Indies, and so on. And that's going to be a real problem to many people. Then some of the rest of the world will get much heavier rainfall, and so on. But it isn't just the size of the rainfall, it's also the intensity of the way in which it comes down. And I needn't tell you about storms in the world. We've seen more storms. Any one storm, you can't really say that's due to climate change and human-induced climate change. But when you get many more storms of the kind we've had in the last few years now, over many parts of the world, we can say with some confidence, this is just the start of a trend towards much more intense storms. And the problem of floods will become greater, and some work on computer simulations are suggesting that by 2050, in many parts of the world, there will be something like a factor of 5 increase in the number of floods and things that we're going to have. And that's a pretty serious number, and and you can imagine how the world is going to suffer from that sort of thing. Floods and droughts, the most damaging of disasters, they cause more deaths, more misery, more economic loss than any other disasters we know. And a factor of 5 would be a big problem. And countries like Africa have very little resource, of course, to cope with that sort of thing at all. And it's going to hit parts of Africa extremely, extremely toughly, I'm afraid. And we will have to do all we can, of course, to help. So that's the story I've just tried to tell you about what's later likely to happen this century. It's not likely that the Greenland ice cap will melt down for a long time, but it could start to melt down, and it did melt down completely, there'd be 7 meters of sea level rise around the world, and that would be that's a big number. And we're talking about very large numbers of environmental refugees wanting to move to places because they can't live where they are anymore. And also, forgetting about people for the moment, there's also species, many species of animals of all sizes and kinds who are going to suffer enormously because they can't move either, and many of them become extinct. So what have we been doing about this subject over the last 30 years? I've been involved in trying to work on a world scale with scientists around the world as to what we can do about it. And the Intergovernmental Panel on Climate Change was formed in 1988 by the World Meteorological Organization, partnering with the United Nations Environment Programme. I was asked to be the first chairman of the Scientific Working Group, which is a wonderful task, but a very demanding one, because we had to try and write reports. Reports would go to governments because it was an intergovernmental panel. Now, lots of people said to me at the time, oh, you don't want it to be intergovernmental, that would be terrible because you'll be influenced in all sorts of improper ways. Why don't you make it something just a scientific body, independent scientific body? And I argued against it and said, well, governments have to be involved. And I was right, actually, because if it's just a scientific body that had written these documents, it would have been ignored by governments worldwide. Fortunately, governments were part of the process, and in fact, the final reports that we had a lot of people, many hundreds of scientists from different countries, writing chapters and developing them and so on, and the final result was to try to come up with a summary at an intergovernmental meeting, where you would have about 100 countries, representatives from 100 countries, mostly scientists sent by countries, but some with lawyers were sent by Saudi Arabia and such like states who are trying to do their best to weaken these things. And we had to agree the summary, which would be typically 10, 15 pages, sentence by sentence, and to do that unanimously because that's the UN style. But we were a scientific meeting and not in any way a political or not supposed to be anyway. So that was a very demanding task to look after, but it succeeded, and we've actually managed to write. The IPCC wrote its first report in 1990, which had a big impact after that because it helped the Earth Summit in 1992 in Rio de Janeiro to come up with a very good program for doing something about climate change, or trying to do about it. And I could tell you a great deal about that business, but I won't go into it in any more detail than that, except to say that it's the fifth report of the IPCC has just come out. It was published in the scientific part was published in December, and the other parts will be published this next month. And the scientific part is 1,500 pages long, A4 size, with many thousands of references in it and pictures and so on. A tremendously detailed account of the whole, what we know about the Earth's climate and what we know about what humans are doing to it at the moment. And of course this has been through this tremendously intensive review process, which was finished up with you have to defend it in front of hundreds more government representatives, not all of whom want to get the answer that you feel is correct. So it's a very demanding process, and it's working very well. And there are crazy politicians around the world who still rubbish the IPCC and say this is just scientists trying to do their thing and trying to get money for their research, and it's, it can't be like that, it won't be like that, and we're not going to believe it, and you don't believe it, do you? And the newspapers pick up these remarks, and it's very hard to get the truth over about these things in the World Wide Web. I must move on and not carry on too long on that sort of issue, but that's there's in 1995 we had a very tough meeting in Madrid, And there am I in the middle holding the Earth. There is Jill Van Myra from Brazil, who was my co-chair, taking the Earth's temperature. And there's Bert Berlin, who was the chairman of the whole IPCC, who was also, and that's what Nature magazine put in their journal. They had a series of 12 meetings that changed the world series, and this got into that series as something that really was terribly important from an international point of view. I was going to say a bit more about the science, but I don't think I really have time to do much of that. But to say, well, our main sources of forcing the greenhouse gases, the aerosols, one of the biggest unknowns at the moment. These things like sulfate aerosols, which come from sulfur dioxide from power stations. You get sulfates in the atmosphere. Those sulfates create little particles which will reflect sunlight and tend to send the sunlight back again and act as coolers, actually, of the Earth's surface. And that cooling is of the same sort of order. It's much less than the warming from greenhouse gases, but it's perhaps 30% of the warming is actually matched by cooling by aerosols and the like. And we have, of course, volcanic eruptions from time to time, which tend to cool the world because of the cooling from the dust from those, and so on. So I mentioned these important uncertainties that we have of aerosols. There's also we've got to learn a lot more about the land surface, how we do our farming and so on, because we can create sources of carbon dioxide into the atmosphere as a result of that, or we can mop it up by the chemistry and the biology of what goes on at the Earth's surface, and that's an important business. Something else which is becoming to the fore too, the oceans are getting more acid because they are dissolving carbon dioxide, and the acidity is not good for many fish or mollusks or all sorts of particular things, creatures in the sea that have shells and the like. And there's a big worry about, because it's getting more acid and it's more acid now than it was getting on for millions of years ago already, because it's been a very steady amount, and so that's something the world is rather worried about. So what can we do about it? And I'm not going to spend a long time on this, except to say, of course, the United Nations got the Convention on Climate Change at that meeting in 1992 in Rio, and we have to both adapt. We've got to adapt to the changes. We can't help but do that. But we also have to mitigate. We have to try and stop them getting worse by cutting our use of fossil fuels. And how can we do that? We can to increase the efficiency in buildings. For instance, we can generate our electricity from other sources, and you're doing that in your islands here. We can try to do something about our agriculture to increase carbon capture. Transport, we have to try and move to electric vehicles rather than ones that burn petrol or oil or gas, for that matter. And that's not a possibility. And we have to halt deforestation. We have a lot of deforestation in the world still, which is it's beginning to halt. But a lot of forests, which are terribly important for the world's creatures and so on, are still under great destruction. So that's a big problem that has to be done too. That's a picture from the UK. That's our Houses of Parliament. In the infrared, it's leaking heat. And the buildings that, I have a number of pictures like this of different buildings that are leaking heat, and we shouldn't leak heat from buildings because we have to try to preserve, not use heating in order to release heating from fossil fuel sources that warms them up. And then we have all the renewable energy technologies, and you'll be aware of all of those, and I needn't say much about them. You've got solar thermal and solar PV, you've got biomass thing, crops and waste, We can have wind devices and tidal. I think the potential from tidal in the UK is large, and we should be doing it. Building tides and so on. We could get, in Wales, for instance, we could get all our electricity without any trouble at all from a set of tidal sources. And there's also geothermal. And there's one from Spain, which I thought I'd put in. This is solar power. This is from a place in Spain, Abengoa. And PV cells here, the last one was. And then we can have, of course, tremendous possibilities in the third world, for instance, of using PV systems to help people in the country. We just bought an electric car, actually very hard to buy, actually. But we just got an electric car that will drive on one charging, supposedly 90 miles. It's not quite that much, we think, but it will get us around locally very well. And but it's not using any fossil fuels, and we should have much more of that sort of possibility. And it's been estimated that from the Earth's waste, particularly from farming waste and the like, agricultural waste, we could get 10% of the world's energy needs, and we should be doing something like that. There's lots of possibilities. What about targets for where we should get to? There's been a lot of talk internationally about targets. In 1996, the European Union suggested that a good target would be the Earth must not get more than 2 degrees above its 2 pre-industrial value. We're approaching 1 degree at the moment. 2 degrees would be a very tough target to meet, but they've stuck to that actually. And there's all world conferences on this issue tend to say we mustn't allow it to go more than 2 degrees. The end of the conference is never we've done things to stop it getting more than 2 degrees, but they're still saying it. And that's a good target to go for. Otherwise, if we do nothing or very little, we're going to get 3, 4, 5 degrees by mid-century or the end of the century, and that really will, as I've tried to explain, that will produce conditions that are really very unbearable for much of the world's populations. And if we care about our children and our grandchildren, and I care a great deal about them, mine, we should be doing something very hard to try to alleviate that problem for them. Can we achieve it? The answer is yes. But let me just show you this diagram where we are at the moment. This is emissions of carbon dioxide into the atmosphere starting at 1990. The red line is a business as usual line produced from the International Energy Agency in Paris. I'll say more about them in a minute. And that's what's going to happen. We're going to end up with, that's going to take us to 3, 4 degrees before the end of the century. If we want to keep to 2 degrees, we've got to go down if I can just try and poke this thing in here. I don't know if I can manage that or not. Doesn't seem to, like, it's supposed to. Anyway, you can see the green line going down, which will take us, get us back to the, which will keep us to 2 degrees or thereabouts. And there you will see lots of things we need to do in order to get back to there. And also, developing countries have to cut their emissions very sharply if we're going to allow the developed countries to actually get any share at all of fossil fuel emissions and fossil fuel energy, which would be the fair thing to do, since we've grown so well. On fossil fuel emissions, we should be really trying to help the rest of the world in a big way. I mentioned the International Energy Agency. They're doing a lot of work on this issue. They were asked by the G8 countries meeting I think in Scotland in 2006. They were asked by them to say, what has the world got to do with its energy systems in order to keep to 2 degrees? And they've come up with thick books every year describing how it can be done. And they're not green people, they're not sort of, they're energy people. They've not been environmentalists or anything like that, but they are very interested in the technologies. And what they say, the messages they put over are very strong. They say we can do it. They say we just have to change the way we get our energy by using renewables or whatever, or nuclear, in fact, is another possibility, of course, for some countries. And they say it won't actually cost us anything if you average it over the next 10, 20 or 30 years, because we will save so much for not having to buy coal and oil and gas. And in fact, the world will be much less polluted. We will have much more secure energy systems around the world because they'll be much more widely distributed. We won't be having wars over oil or whatever. And this is this body which is really studying it from a technical engineering point of view and producing answers that are really politically very strong, but politicians are not taking much notice at all of that. Have I... why not just move on? Can you just... that back for... Oh, thank you. I've got rid of that for me. Thank you. Lovely. No, just some carbon dioxide emissions, what happens in different countries. This is tons per person, about a couple of years ago. The USA, of course, and Canada are the biggest culprits. Europe is not so good. China is well over 6 now and getting greater. But China is working terribly hard at renewable energies. They want to be the world supplier of renewable energies. They want to supply PV, solar PV, and lots of other sorts of things too. They're working hard at it. They know about the climate problem. They have a very good climate research institute in the middle of their government which knows about it. So that's good news, actually, and we should be taking notice of how to... Oh, I'm back again with the same problem. What? Thank you. Press the wrong thing. So there's a real moral imperative there. We've grown in our wealth in the Western world so much. We didn't realise the damage we were doing, and we should be doing everything we can to reduce the damage and to assist poor countries. We should be becoming much more sustainable. Because if we're not becoming sustainable, we're cheating on our children. We're cheating on our neighbours, and we're cheating on the rest of creation. Can we afford it? I've just said the IEA message. Can we afford the energy revolution? We can afford it, but we've got to get on with it. We first to tackle poverty. The world poverty is terrible, and then we can get on to things like climate change. The answer is no. Because if we don't tackle climate change now, we'll have so many more poor people. And that's a very strong message. And hasn't the recession, we're all suffering from it, has to have top priority, and then we can go to climate change. Well, that would be stupid too, because in fact to tackle climate change would be a very good thing for our economies, because it would really bring all sorts of resources into all sorts of ways. Well, can't we wait and see? No, we can't. This is obvious and the sort of thing I've tried to say to you, that we can't do that. I just mentioned a fierce urgency of now, and quote from Martin Luther King in 1967. I'll finish up with a slide from space. There's the Earth from the Moon. And there there's our beautiful Earth. You must do everything we can not to spoil it, but to preserve it and to look after it and to preserve all the creatures on it, all the people and all the creatures. That's an absolute imperative too. So thank you very much for your attention.
Okay, so thank you very much for your nice and suggestive talk. So now there is time for questions.
Could you talk a little bit bit about the effect of methane.
I'm sorry, can you...
The effect of methane, rather than
yes.
CO2?
Yes, well, methane is a greenhouse gas. It's the second most important greenhouse gas. It is something like 20% of the whole problem, and we've got to do something about that too, yes.
Even worse, possibly problem, in the sense, the Russian tundra is also...
Well, it's a big problem in the agricultural area, of course, because cows are producing methane.
That's included in the models, of course. The methane is included in the models.
That's in the model I've described to you, yes. It's not all about just carbon dioxide. All the greenhouse gases are there. But methane is a problem because the world's beef production is going up enormously. People are eating beef on a big scale, and beef produces methane. So I
believe it's a big problem also because the radiative forcing of methane is much higher than CO2, I believe. Is that correct?
Sorry,
so the effect...
I don't hear very well.
The effect of methane is much higher than CO2 per particle. Is that correct? So the radiative forcing, the greenhouse effect of methane is higher than CO2. So
per molecule,
right.
Yes, it is.
Yes,
that's right,
yes,
sure.
yes, per molecule.
Per molecule, yes, but it's not. There's not as much of it. That's right. Of course, it is. It's a lot bigger, very much bigger. Yes, because we've got a lot less methane there. So.
In one of your graphs, you saw the effect on temperature of the volcanoes, Pinatubo, in some of your graphs.
Pinatubo, yes.
Yes, Pinatubo, and other volcanoes. And apparently, the prediction was a very high peak in temperature and then decreasing. Is that observed? I mean, in one of the graphs you showed, there was the predictions by the models of the temperature change caused by the volcanoes.
Yes.
There were some volcanoes there, and I noticed a big peak, a big rise in temperature,
yes,
and then a decrease. Yes. And apparently, is that observed?
Yes, it's observed. Yes, those that come from observations actually, and you can simulate it also. First of all, you get a massive amount of particles inside, small particles going into and gases going into the upper atmosphere. They live there for the order of 2 to 3 years. And gradually get come down and get washed out and so on. So the initial impact is over the first year or two, and then it gradually diminishes from big volcanoes. Yes.
My question is because possibly you are always struggling against people telling that most of the effects are, for example, the changes in solar irradiance or of the effect of the volcanoes. Those are not non-human related.
No, that's not. Sure, that's not human related. That's true. But of course, volcanoes are tending to cool the Earth as it happens, and then you have the variations of the sun, which I could say more about, but which are there, and which but they're small compared with the greenhouse gases. A lot smaller.
So just a comment now. In a sense, it's unfortunate that the United States, according to the predictions that you showed here, were not having big temperature increases effect or floods. Apparently, the United States, for some reasons, will not have the worst disasters in the next year. So, in a sense, this is unfortunate, no? Because possibly they are not, they are not taking very seriously the. Do you think? Because of course the political system in the world is also a very complex system as the atmosphere. It's also a very big, very difficult and non-linear system, and you are struggling against this political system. And my comment is that if you see the predictions for example, the increase of temperature, of the frequency of floods in the area of North America, apparently, I don't know because I don't know what the reason is. Apparently, they will be less affected than the rest of the. Have you noticed that?
I'm sorry.
If you, sorry. My question is, please translate it.
Yes. Yes. Oh, well, sure. Well, we can't organise these things. We'd love to organise some really big effects, like in North America, but they had a very big storm last year in North America and New York, and that's certainly got the mayor of New York talking about the likelihood of this being human-related. And it helped, I think it helped Obama to get back into the White House, incidentally, yes. So there is a political reaction, I know. And, yes.
Okay, thank you.
Thank you very much for the talk. It has been excellent, because we have heard some things that you have told us today said by other people, but to be said by somebody who has participated in the research is a privilege. So thank you very much for your talk. And I have a question, because you have said that the oceans keep a lot of the heat. Mm-hmm. And in some of your slides, you said that it will take centuries for this to be released, for this energy to be released. Mm-hmm. So my question is, even if you convince people to change the regulations, the energy, and all these things, so that you are able to stop 2 degrees, I mean, to go down in the increase of the temperature, the oceans are still going to be very cool, very hot, sorry. And then, do you expect that all these events that we are suffering, like storms, cyclones, I don't know how to say, all these things are going to keep happening? Yes. No matter what you do?
Oh, well, not no matter what you do. If you don't stop doing it, then it will get worse. Right?
No, but my question, I understand.
A lot of people say, oh, it's so bad we can't do anything, let's stop, you see. And that's rubbish, because unless we stop doing what we're doing, then the whole situation will get a lot worse. Yes, there's still more to come by what we've done, yes.
I know
but that will diminish with time because of the...
I understand that if you do things, things are going to be better in the future. My question was more simpler.
Yes.
So if the ocean is going to be hot, no matter what you do, are there plans, or do you think that even though you do something, we are going to have a long period of those so-called disasters that we are suffering now? Because if this is the case, at the same time, we should also have to be prepared for facing the so-called with a period of temperature of things in the near century.
Yes. Okay, for instance, you see, we are committed almost certainly to sea level rise of, I've said, the order of a metre this century, maybe less than a metre. Certainly we start to do something about it, but that will go on for centuries. And the sea level rise will continue to be a problem, and an increasing problem. And because it will begin to, people will get used to the sea level rising and having to do, because it will be part of the existence, but it won't be getting worse as far as the slope won't be getting steeper. So we'll know about it and we'll have to do things about it, but it will, of course, much of the world's land near the ocean will be suffering from that for centuries to come. And people should realise that. And unless we stop, doing something now, then that's going to get a lot worse, sure.
There is time for 1 or 2 more questions.
Okay. In your models, have been taken into account in the non-human effects their long time period effects related to astronomical...
Yes.
Okay. The small variation in the sun irradiances and small variation in orbits of the planets and so on. in the period of thousands of years, even more?
Yes,
Take into account in the projection of the climate change?
Well, if you go back over the last 1,000 years or something of that order, there have been variations of the sun, which people, of course, we never didn't measure with that accuracy, but people have inferred the variations which might have occurred over that period, and those are small compared with the sort of variations we're beginning to get because of the greenhouse gases. So we don't expect the sun to change in a way that's helpful to us, either or makes it a great deal worse, or is very helpful to us. But we want to keep notice of it. And of course, the sun has not. We had the last solar cycle was an unusually weak cycle, and one reason for the fact that the temperature has not gone up since 2012 as fast as we expected is because it was a weak solar cycle, and that's one of the reasons why it's not changed as much as it might have done. Whereas people have said, well, of course, you're just talking nonsense, it's not changing, not going to change anymore anyway, because we had a very strong El Nino event in 1998, which is an event in the Pacific Ocean and so on, which tends to put up the Earth's temperature for a year or two. And that came about in 1998, and 1998 is almost still the world's warmest year. And that's a few years ago now. And people said, well, it hasn't gone up since 1998, so it must be levelling off, and so we're fine, you see. And they don't say refuse to take notice of these other phenomena which are causing these big variations in the atmosphere, particularly. But I think the ocean story, which we're now getting rather well clued up about, which is now telling us that the oceans are warming, and we're measuring that, and that's a more stable situation in a way than we got in the atmosphere. Then that really tells us, the two pictures I showed from the oceans, the one with individual areas of the Earth, and the other one with the blue blocks on it, as to how much energy was going into the oceans. That really is telling us that it's a long period business. It's not something that's going to go away in 5 years at all. You can't conceivably do that because the story of the last 20 or 30 years is such a consistent story as far as the oceans are concerned.
Hi. Thank you for the talk, John. Just one quick point I'd like to query you on a bit. You talked at the end about kind of decoupling issues about global issues of poverty and climate change and economics and power production, and prioritizing them in a way and addressing them in a priority. I suggest maybe these are problems that need to be solved in conjunction to effectively address them. So by addressing poverty, energy production, sustainable production of food altogether, you could more effectively address them rather than ordering them and doing one at a time.
Yes,
and
I'll agree with that completely, but it was, I just put the points one at a time.
Okay.
But they all belong together, of course, really. We've got to behave sensibly, yes.
And I wondered if you could maybe comment on how you envisage a society 2.0, if you will, or a society that would function sustainably at a global level. So how you think society could work where we could have some kind of sustainable model.
Well, that's, you're asking a very good question, of course, how it can be done. And it's and people have to change their attitudes to think sustainably about not what's happening to me or to my family, or at least if you take your family, of course, thinking about them sustainably, immediately it takes you into the future, and then you're really concerned about it. So you've got to get people to think more in the long term, you've got to get politicians to think in the long term, which most of them don't, and so on. So there are lots of changes that have to occur within our political systems, with our political thinking, with our economic thinking, because the IEA said very clearly, from an economic point of view, it can be done, and it will make us all very much better. But that's not listened to at all by the people who make the decisions. Or I've not got any evidence that all those marvellous volumes from the body which belongs to governments, actually, they don't take any notice of it, because they have different agendas which are set by people who don't know anything and don't want to know anything. Now, how do we get over that? I'm not quite sure. We've got to educate the media too, actually. We've got to try and get the media to speak the truth, instead of speaking the first thing that comes into their head that sells newspapers. And it's all about truth, actually. What is correct? And science is very much about truth. Trying to say, I believe this because the evidence is all there, and all that sort of thing. And so it's a battling for that sort of thing. But I'm not a very good battler in that way, I don't think. But we've got, if enough people really get going about it, and the right sort of people get going about it, it does make a big difference. I often say, politically, if only, the United States and China would get together, they could, between them, because they're the two biggest emitters now of greenhouse gases, if they could get together, and they could solve the problem by agreeing, very simple things, actually. But as it is, that seems very difficult. China is selling all these goods to the developed world, and we're buying them very cheaply. And we don't realise when we buy all these fancy, gadgets from China, that in fact we are supporting an industry which is based on coal. And in fact, it's been argued for the UK that if we, all the Chinese imports of gadgets and the like, which we bring in each year, that is putting up our emissions of greenhouse gases by 20%. That's taking away all the work that we're doing in the country trying to cut it down. Now, that's a very simple problem to solve if only the right people got together to solve it.
So I think we are going to stop here the talk. So thank you again very, very much to our speaker. And just remember that now we can continue speaking with him at the library, at the canteen. Okay.
Yes. 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 Well, it's good. Right, I was getting rid of this. I can get rid of that gear, which would be nice.